In part 4 of this video series, we'll be looking at the concept of the phasor, and this is actually the complex representation of a sinusoidal voltage or current. Let's say we have a voltage Vm cos omega t, which can write as Vm cos omega t plus theta, because at t equals to 0 the angle of this cosine wave is 0 degrees, and we can represent this cosine wave as in a complex form as Vm angle 0. And if we have a current Im cos omega t plus phi, we can represent this current in complex form or complex representation Im angle phi, and this complex representation is known as phasor. And the transformation steps are actually, if you have a sinusoidal voltage or current, make sure it's in cosine form. If it's in sine, subtract 90 degrees to make it a cosine. And if it's Im cos omega t plus phi, we can represent this cos as the real part of the Euler's identity. And we know that Euler's identity has a cosine part and the sinusoidal sine part. So cosine is the real part, so we can just write real part of this thing Im e to the power j omega t plus phi, and then we have real part of Im e to the power j omega t and then e to the power j phi. So it is understood that Re and e to the power j omega t is written right next to this Im e to the power j phi. We simply don't write it anymore. We just assume that this real and this e to the power j omega t is written right next to every current and voltage, and then we just write Im e to the power j phi, which is the Euler's form of the phasor, or we can just write it in the polar form Im angle phi. And if we want, this is the polar form of the phasor, and this thing has e to the power j omega t written right next to it, but we simply do not write it. It's just assumed to be there, and whatever circuit we are working on, it's assumed that, and it's actually mandatory, that all the voltages and currents are operating at the same frequency, which is omega radians per second. And this thing Im angle phi, that is known as the polar representation of a phasor. If you want to have the rectangular representation, you can just write this thing as Im e to the power j phi can be written as Im cos phi and then plus j Im sin phi. So if you, and that is the rectangular form. If you are given the rectangular form of a phasor and you want to convert it back into polar form, you just write the, you just square the real and imaginary parts, which is x square plus y square under root, and then we take the tan inverse of the y over x. So let's say if we have a voltage of 115 angle minus 45 degree volts, and we know that this voltage is rotating, or this phasor is rotating at 500 radians per second, so we can write this thing as 115 cos 500t angle minus 45 degrees. Or if it's in the sine wave, you can just have the component of a 90 degree right next to it, so you can just add 90 degrees to convert into sine. Now what this phasor looks like graphically is something like this. So this phasor is rotating at certain revolutions per second, or if we know that how these revolutions per second, or how many degrees per second, or how many radians per second. This is essentially the same way to represent the angular velocity. The angular velocity is given in radians per second. So this phasor is maybe completing one revolution every maybe 2 seconds or 3 seconds. So we can just figure out how many degrees per second or how many radians per second. But the point is that this is the complex representation of a phasor with e to the power j omega t component. So the magnitude, the length of this phasor represents, this, or the radius of this circle actually represents the length of the phasor, or if you're talking about voltage and current, it represents the magnitude of that voltage or current. And the angle which we were talking about, that's, let's say if you have the this 115 angle minus 45 degrees of phasor, that means 115 is the radius of that phasor, okay, and this minus 45 is the angle of the phasor at t equal to 0. Angle is constantly changing, but what we're talking about is that what is the starting angle at t equals to 0. So we just draw this phasor as 115 and angle minus 45. That's the starting point of the phasor, and it's constantly rotating. And this thing has e to the power j omega t written to it, so that means that it has a magnitude as well as it has a direction, and by direction we mean it has the direction which is rotating in the counterclockwise direction. That's why we represent these phasors, even though they are rotating, as kind of we use vector representation to represent these phasors. And we can use the vector algebra and vector analysis to figure out the addition and subtraction of phasors, and multiplication and division of phasors. So this phasor, I mean this thing, it has e to the power j omega t written right next to it. So if I just rotate this figure, it looks like this counterclockwise rotating spiral. And in another part of this video series, I will be explaining that if the phasor is rotating in anti-clockwise or counterclockwise direction with respect to time, we call this phasor as a positive frequency phasor. Okay, and if the phasor had been rotating in the clockwise direction, we will call this thing a negative frequency phasor. And I'm going to explain why we need positive and negative frequencies to represent a real signal, but that's topic for another video. Now this thing has e to the power j omega t. Okay, so omega implies some radians per second, some rotation. It's rotating due to positive omega. This thing is rotating in anti-clockwise direction. Now if I have this figure, and if I see this thing with respect to real versus time, if I rotate this figure, okay, if I rotate this figure and I see only real versus time, I see a cosine wave. Now if I rotate this figure and see this figure with respect to imaginary versus time, this is imaginary axis, and if I see with respect to imaginary versus time, I see a sine wave. That means that sine and cosine are part of the same rotating e to the power j omega t, or this complex representation has both these cosine component as well as the sine component, the real component and the imaginary component in it. That's why instead of using the word sine and cosine separately, we use the word sinusoidal. Now coming back to this representation, I'm going to explain how this real and e to the power j omega t actually works in another part of the video, but let's just take that whatever we have in a time domain representation, we can represent this thing in frequency domain. I mean this phasor representation is actually a frequency domain representation because every voltage and current is assumed to be operating at the same frequency. So I mean, let's say if we are living in let's say we take an example of Karachi, and the city code or the telephone code of Karachi is 021. That means that if you are dialing some landline number or some PDCL number as we call it, we do not dial 021 before dialing the number, because it's understood that if you are dialing it locally, you are already in the same city code, and that's why we do not write e to the power j omega t right next to every voltage and current. Is just assumed to be there. Now if we have the like time domain representation, 100 cos 400 t minus 30, we can just write 100 angle minus 30 volts, and the radian frequency 400 radians per second is written right next to it, but it's not specifically or explicitly identified. And e to the power j omega t is written right next to it, and that means this phasor is rotating at 400 radians per second in anti-clockwise direction. Now coming to the examples, let's say if you have a resistor and V equals to Ri, we can transform these voltages and currents into phasor form. Then we have V equals to Ri, and we write in bold letters to emphasize that we are talking vector representation of a phasor, because phasor has a magnitude as well as the direction of rotation. That's why we can use the vector representation. I mean, the derivation is given in your book that Vt can be written as the real part as well as the imaginary part. We just represent this Vt as a complex form, and this is complex representation of the source or the source voltage, and the current can be written as a complex form. So the real part produces the real part of the response, the imaginary part produces the imaginary part of the response. So we can write Vm e to the power j omega t plus theta equals to Rit, and same thing. So if we divide the whole term, or we know that all of these terms, that Vm e to the power j omega t e to the power j theta, we can write Vm angle theta e to the power j omega t, and I can write Im e to the power j omega t and e to the power j phi, which is Im angle phi e to the power j omega t. So this e to the power j omega t is written right next to every voltage and current term, either in mesh equation or in nodal equation or any KVL or KCL equation. So we can just write this thing as V equals to Ri, and if I do take the ratio of V upon I, that is R. So this resistance or this Ohm's law holds true for time domain as well as the frequency domain representation. So if we have IT equals to, let's say if we have this 8 cos 100t minus 50 degrees volts across a 4 ohm resistor, the current would be, you just divide this whole thing by 4, you have 2 cos 100t minus 50, or you can just write 2 angle minus 50, and it has e to the power j omega t written right next to it. Inductor has the same, Vt equals to Ldi over dt. Let's say if we have this voltage Vm e to the power j omega t plus phi, and this thing is with an angle, this thing is theta and this thing is phi, and if we take the derivative, this e to the power j omega t and e to the power j phi, I mean that's a constant, and e to the power j omega t has a derivative of j omega e to the power j omega t. So we have this equation with j omega written right next to it, and if we divide the whole terms, or if we just assume that e to the power j omega t is written right next to every voltage and current, we have and we do not write it, or we just divide both sides of this thing, I mean this thing remains, and this Phasor relationship is V equals to j omega Li, or if we take the ratio of V to I, inductor in frequency domain has ohms of j omega L, and this j only represents the phase difference between voltage and current of 90 degrees. Same thing happens with the capacitor, and if you take the integrated derivative, this I over V equals to j omega C Siemens, or V upon I equals to 1 over j omega C ohms, and this j only represents the 90 degree phase shift between current and voltage, or I leads V by 90 degrees in a capacitor, because we know that j is under root minus 1, and if we multiply any vector by minus 1, we have the phase, we have the, let's draw this thing. If we have I mean, let's say if we have, let's quickly draw this thing as if we have a vector of, and we just multiply this thing by minus 1, this whole vector will shift its direction. If we multiply, I mean this is the same thing as multiplying this vector by under root minus 1 twice. So if I multiply a vector by under root minus 1 just once, okay, so this vector will shift, sorry for the drawing, will shift by 90 degrees in anti-clockwise direction. So that means multiplying anything by j, you are just merely shifting the direction of the vector by 90 degrees. So j represents 90 degree rotation in anti-clockwise direction, and minus j represents 90 degree rotation in clockwise direction. So coming back to this time domain and frequency domain representation, is time domain inductors and capacitors are written in this form, but in frequency domain they could have the V equals to j omega Li and V equals to 1 over j omega C I, and this V and I are all phasors, and these phasors are also used in KCL laws as well as the KVL. So we can write the mesh and nodal equations in complex form using phasors. So that means the original problem was that we had to deal with the differential equations whenever we were talking about, or whenever we had to analyze the circuit in time domain. So we had this weird looking differential equations even if we had to solve a simple RL circuit problem. But now if we have the phasor representation of voltage and currents, and the frequency domain representation of the inductors and capacitors and resistors, our differential equations take the form of simple algebraic equations. So this KCL and KVL, they have the simple form of but they are complex, but they use j and minus j with it, but they take the form of the simple algebraic equations which we can solve really easily. And the last thing we have to cover is in this part of the video is impedance and admittance, and V equals to Ri, so I can just take the ratio of V and I for each resistor, inductor and capacitor, and these things, the ratio of these voltage and current phasors is the impedance of the uh, resistor, inductor and capacitor. So this J, I mean this voltage to current ratio actually represents the ohms of this inductor and capacitor in frequency domain, and it does not mean that there are some complex quantities. I mean J only represents the 90-degree phase shift between voltage and current of the inductor, and here it is minus 90 degrees because 1 over J is minus J. It represents the minus 90-degree phase shift between voltage and current for the capacitor. But inductors and capacitors, if they are excited by a sinusoidal source, they do offer some ohms to, depending on the frequency and depending on their value for inductance and capacitance, they do offer some ohms to the current or the sinusoidal current. Okay, so if we have the series impedance combinations, because impedance is purely a frequency domain concept, so if you have multiple impedances in series, you can just add them together. I mean, no matter what the sign is, because 1 over J is minus J. And if you have parallel impedance combination, we can use the very same formula of R1 R2 divided by R1 plus R2 as Z1 Z2 divided by Z1 plus Z2. The imaginary part of this impedance is known as reactance, and the real part of this impedance is known as the resistance. So, and the last thing here is the which we call the admittance, that is y equals to 1 over z, and we have 1 over r plus jx. So the real part of this admittance is known as the conductance, and the imaginary part is known as susceptance. But watch out that 1 over r does not mean g and 1 over x does not mean b. I mean, you have to take the inverse of the whole number, a whole complex number, to figure out the real part and the imaginary part of the admittance, and the unit of this thing is in Siemens or MHOs. Okay, and lastly, nodal mesh analysis. You can just write the KVL and KCL equations, and every term has using simple Phasor notations, and every term has e to the power j omega t understood to be there, and every current and every voltage term has e to the power j omega t right next to it. So all the superposition and all the Thevenin theorems and all the source transformation, everything, I mean, they could be done in the frequency domain just by writing the omega right next to it, and I mean in one part of the circuit somewhere, and this assume that all the components and all the voltages and currents and all the ohms are at one frequency. So if you are that's how we avoid the use of differential equation and use the simple algebraic equations to solve for the unknown voltages and currents in a circuit.